Having explained what this interpretation of physics is, I will now begin to discuss some of the implications of this idea, starting with a possible explanation for dark matter. You see, most of the mass in the universe does not originate from the regular visible matter we can easily observe. It instead comes from something else entirely, something that we call dark matter. The origin and nature of this dark matter is one of the biggest mysteries in physics right now. While a number of possible answers have been proposed, no theory has so far been able to fully explain what dark matter is. They all fall short in one regard or another. So I'd like to discuss the possible explanation that comes out of this interpretation of physics, which is that dark matter, like everything else in the universe, is just motion in space-time. This motion would be created by the interactions and distortions of regular matter. Researchers are able to calculate, within some margin of error, the amount of ordinary matter that exists in the universe, and this quantity falls far short of the amount of mass actually seen in the cosmos. This extra mass of unknown origin is called dark matter. This unexplained mass can be seen in a number of different observations, like the rotation curves of galaxies, which is the rate that objects orbit around their galactic center. It was predicted that objects in a galaxy would have slower orbital velocities the further away from the galactic center they are. This is, after all, how solar systems work, where the orbital velocity of planets drops the further away from the Sun. However, what is actually observed is that most galaxies have a flat rotation curve, where objects in the outer orbital ring are traveling at approximately the same speed as objects in the inner orbit. In order to explain this discrepancy would require more mass to be present beyond just the ordinary matter we can see. Something similar can be seen with how galaxies themselves travel faster within galaxy clusters than they should given the amount of regular matter they contain. If their mass came just from ordinary matter, then they should move much slower than they do, indicating that more mass must be present than can be explained by ordinary matter. There's also direct evidence for dark matter from gravitational lensing, which is where the gravitational effect of massive objects can bend the trajectory of light. This causes visual distortions around large masses. The more mass of the object, the more it warps spacetime, and the more the trajectory of photons passing nearby get distorted. By analyzing the amount of lensing around galaxies and galaxy clusters, the effect of this extra mass can be directly measured. And the amount seen is more than what would occur from just the mass of ordinary matter alone, meaning dark matter must be present. There's even evidence for dark matter in the cosmic microwave background radiation. There must have been extra mass present during this time period to account for the shape and distribution of matter. By analyzing this data, it can be shown that more mass must have existed beyond regular matter to explain the distribution seen in the cosmic microwave background. Dark matter must have been present. And lastly, the universe could not have come together to create all the structures we can see today in the time that they did unless more mass was present in the early universe. With just ordinary matter, it would have taken far longer for these structures to form. Fewer galaxies would exist today, and those that did would be much younger than they are. Basically, not only can we directly measure this excess mass, the structure of the universe could not exist without it. Researchers have been able to calculate the total mass energy content of the universe, and it appears that the universe is made of about 15% ordinary matter and about 85% dark matter. Accounting for all the energy that is present in the cosmos, the universe is made of 5% regular matter, 27% dark matter, and 68% dark energy. Dark energy being the energy required to explain the increased rate of expansion of the universe. Dark energy isn't entirely understood either, but this video will mostly focus on dark matter, as I have more to say on the topic. The oldest and most popular theory is that dark matter is some as of yet unknown particle or class of particles. It's a very direct explanation. There's missing mass in the universe. Mass largely comes from particles, so dark matter is probably some new particle. These particles would have been created at the beginning of the universe and would have been directing the formation and movement of the cosmos ever since. In broad strokes, this works as an explanation, but there are problems in the details. Many of the observations that can be made of dark matter, or of its effects, do not line up with what would be expected if it were just another particle. For instance, the distribution of dark matter is too clumpy for it to come from any proposed dark matter particle. And dark matter particles don't explain the relationships between the rotation curves of galaxies and the amount of ordinary matter they possess. And things like the bullet cluster do not behave as if dark matter was just another particle. and a dark matter particle has yet to be discovered. So while still the most popular theory, it does not, as of yet, provide a full explanation. The next leading theory is modified Newtonian dynamics, often referred to as just MOND. This is a claim that the laws of gravity as we understand them are incomplete. That while accurate for parts of the universe, these laws change at the extremely low accelerations seen in galaxies and galaxy clusters. The modifications to the laws of gravity are actually quite simple and do a pretty good job at describing a number of observations. However, modified gravity starts to break down at the scale of galaxy clusters and above, and it does a poor job of explaining the CMB data or structure formation in the early galaxy. And there still isn't a good explanation for why exactly gravity would change properties at low accelerations. It's just an assumption used to justify the math. Plus, there's the problem that a number of galaxies have been found that contain little or no dark matter at all, which shouldn't be possible with MOND. And just like dark matter particles, MOND can't fully explain the bullet cluster. Some researchers have tried solving some of these problems by adding more adjustments to their equations. So at the scale of galaxy clusters, different equations are used to fall better in line with observations. And to better explain the CMB data, completely different equations are used. But at this point, MOND stops being a simple coherent theory and begins to look more like creating a number of math equations ad hoc that can each approximately describe a single phenomenon, meaning it lacks the proper framework to draw any conclusions or explanations from. So neither dark matter particles nor MOND are currently able to fully explain dark matter. There are other alternative ideas about dark matter, but they're not worth talking about. However, I would like to mention one in particular as it brushes up against the ideas I am going to discuss. A few researchers have come up with the idea that dark matter can be caused by the gravitomagnetism of black holes. This isn't the idea I have in mind. However, gravitomagnetism is a component of this interpretation. So I'll use this hypothesis to explain the concept. So what is gravitomagnetism? All large-scale objects like planets, stars, and black holes warp space-time around themselves as a result of their mass. But these objects are not usually stationary, they tend to be moving and rotating on an axis. As a result, the space-time being warped is also being twisted as these massive objects move, creating an effect similar to a vortex. This is called gravitomagnetism because it can approximately be described using Maxwell's equations of electromagnetism. This twisting of space-time is called frame dragging. This is a real phenomenon in the universe. It also tends to give objects more mass, which should make some sense, as mass is energy, and this effect is about putting more energy into the distortions of space-time. Since this is a real phenomenon that can produce extra mass, some researchers try to see if it could explain dark matter. The problem with this line of research is that, at least as far as I saw, it makes the assumption that it's only the frame dragging of a galaxy's black hole that causes dark matter. This results in a number of problems. First, for this to work, the effects of gravitomagnetism would have to be several orders of magnitude greater than what's so far been observed. Otherwise, the frame dragging caused by a black hole is not enough to explain the mass of dark matter. And second, this does not provide any answer for dark matter outside of galaxies with black holes. It says nothing about the early universe or CMB data. So this model can't be a full explanation for what dark matter is either. I personally feel like it oversimplifies the universe, because while I believe that gravitomagnetism is a part of the explanation to what dark matter is, I don't think it's just frame dragging from black holes. Because I think that all the other motion and interactions involved in a galaxy should also be considered. What I want to propose then is that maybe dark matter in galaxies is caused from the motion and interactions that occur between star systems, their black hole, and all the other regular matter inside of that galaxy. Because not only are black holes warping space-time, but so too are each individual star system. Let's first go back to mass, which is an amount of energy that exists in a region of space. While particles have a rest mass, an amount of energy from simply existing, this is not where most of it comes from in regular matter. Very little of the mass inside of a proton or a neutron comes from the rest mass of their quarks. Instead, most of it comes from the bonds that form between individual quarks, which is mediated by the strong force. These bonds produce a great amount of energy which is experienced by us as extra mass found in an atom. So most of the mass of regular matter comes from the interactions of quarks and not the quarks themselves. In much the same way, dark matter would then be space-time fluctuations that exist in the empty space between massive rotating bodies. There's frame dragging from gravitomagnetism, which I've already discussed. Stars are massive rotating bodies, so they also twist and warp spacetime as they move. Beyond this, massive cosmic objects can create gravitational waves, which are ripples in spacetime that radiate outwards from their source. They can be created in a number of ways, including from the interactions of two massive orbiting bodies. The more massive the two objects, the stronger the gravitational waves they can create. So as the Earth orbits the Sun, they create gravitational waves, although only minimally since the Earth has such a tiny mass. But two or more massive stars orbiting each other will create gravitational waves of some substantial strength, while two black holes that are orbiting each other would produce even larger waves. In addition to these direct gravitational effects, star systems will also move and influence matter and energy around themselves as they travel. The influence of our Sun projects far out beyond our planetary system in a shell called the heliosphere, which is made from a star's magnetic field and solar winds. It's the outermost layer of the Sun and acts as a barrier to most of the cosmic rays and dust coming from the galactic medium. So as a star moves, its heliosphere interacts with matter and energy around it, redirecting it away and around itself, distorting and moving matter and energy as they move. What I want to propose then is that when there's a large number of star systems that are in close orbit to one another inside of a galaxy, these distortions can interact with each other to create even greater distortions. That star systems in a dense and active galaxy aren't moving through a static block of spacetime moment to moment, but rather through regions that are filled with distortions and fluctuations created by all the motion of other massive bodies. As each star system moves, it distorts spacetime, warping, twisting, and creating gravitational waves. As it travels, it deflects cosmic dust and energy away and around itself. A nearby star system could then travel through these distortions as well as creating their own. And any subsequent star system would also travel through these distortions while creating their own. And all of this is happening alongside the frame dragging created by the black hole or black holes of that galaxy. The idea then is that this could potentially create a flow of spacetime within a galaxy through which star systems travel. This spacetime flow would be what increases the orbital velocity of star systems. Which isn't to say that there isn't extra mass here, because mass is just the amount of energy in a particular region of space or certain structure. If these extra fluctuations exist, as I have described, then they would represent more energy in the galaxy. There would be the interactions between cosmic objects and the energy from their increased movement. One reason this kind of explanation doesn't receive much attention is that gravitational interactions diminish in strength dramatically from their source. Even gravitational waves created from the most energy-dense interactions between supermassive black holes will only have an incredibly insignificant effect on Earth. But it still has an effect. It still exists. And it's not just this one event that is distorting spacetime, as fluctuations from all of the hundreds of billions of other star systems within the Milky Way galaxy would be impacting Earth as well. Which isn't speculation on my part. There's real work being done to find and study the gravitational wave background. The universe is just filled with gravitational disturbances. I just want to propose that if there are enough massive bodies in close enough proximity, then it may be possible for their gravitational disturbances to interact and build on each other. Which also means that if this were true, then we should expect to see little to no dark matter in places where there's either too few star systems or galaxies, or where these objects are too widely dispersed, which would be consistent with observations. There are some galaxies that have little to no dark matter at all. This is usually seen in diffuse galaxies, which either have less matter and fewer stars than a normal galaxy, or the matter that it does contain is more spread out and less dense. The amount of dark matter in these diffuse galaxies seems to be linked to how many globular clusters they contain, which are small regions that are dense with solar system activity. A correlation not only between dark matter and regular matter, but with star systems and star system density in particular. Which goes even further, as there's a direct correlation between the rotation curves of a galaxy and the amount of normal matter present. But not only that, this correlation further holds between a galaxy's luminosity and its rotation curve. There's just a strong correlation with the number of star systems that a galaxy contains and the amount of dark matter. While MOND struggles with some of these problems, this isn't a problem for dark matter particles, where the explanation is that dark matter interacts with regular matter gravitationally. So areas with a lot of dark matter cause large amounts of regular matter to accumulate to form stars. If dark matter particles aren't present, then fewer stars are created in less dense clusters. The interpretation I am discussing would reverse this causation. It's because of the density of star systems that interactions occur, which creates dark matter. When there are too few star systems, or they are too dispersed, then these interactions don't occur and dark matter isn't created. This would also be a consistent explanation for the bullet cluster, which is the aftermath of two galaxy clusters that passed through each other. It's not really a collision, as space is mostly empty, and very few physical impacts actually took place. Almost all of the star systems within the two clusters just passed through each other and continued traveling in the same direction. But from this interaction, most of the cosmic gas, which makes up most of the mass from ordinary matter in these clusters, was slowed down and ended up in a region between where the collision took place. So most of the ordinary matter, which is shown in red, ended up in the middle of the two exiting clusters, while most of the mass, which largely comes from dark matter shown in blue, just continued to pass on through. But it's not just dark matter in the blue regions. This is where most of the star systems are located. Again, a strong correlation not just with regular matter, but with star systems in particular. This interpretation would also help explain the difference in the expectation of rotation curves between solar systems and galaxies. While the phenomenon that I have identified, like frame dragging and gravitational waves, are all seen at the planetary scale, their effects are too small to accumulate into anything more than small shifts in the total mass energy. This is only compounded by the fact that solar systems have fewer interacting massive bodies. Ours only contains 8 planets, some asteroid belts, and 1 sun. So there are fewer massive bodies with weaker space-time distortions. On the other hand, the Milky Way galaxy has some hundreds of billions of star systems orbiting a black hole. These objects are more massive and more numerous. So the fact that the rotation curves are different between the two shouldn't be a big deal. This framework should also scale up fairly well to larger cosmological objects like galaxy clusters, which are groups of typically hundreds of thousands of galaxies that are held together through gravity. They travel faster in their orbits than they should given the amount of mass they have from regular matter. To begin, the extra mass in galaxy clusters should already be accounted for because of the dark matter that exists within most galaxies. It's largely just MOND that needs different explanations between different cosmic scales, as it's based on the mathematical model of their motion being wrong. So it may be that they don't produce any more mass beyond their component galaxies, that the mass of a galaxy cluster is just the mass of the regular matter in their galaxies and the dark matter they create. Even though no extra mass is created, this still creates an even larger dark matter halo that surrounds the entire galaxy cluster, because it's built from the motion and interactions that exist within each galaxy. But it could also be that the interactions between galaxies within a cluster could create even more dark matter. For this to be the case, the interactions between individual galaxies would need to create additional distortions in space-time. Beyond galaxy clusters, dark matter filaments would just be gravitational densities that can exist between different galaxy clusters when their gravitational fields and dark matter halos get close enough. If dark matter is just distortions and movement of space-time, then when two galaxy clusters are near to each other, their distortions can interact, forming a bridge between both structures. Or if two galaxies form near each other, they can maintain a bridge of gravitational filaments between each other. Or at least that's the idea, that these filaments are formed from the interactions between galaxies and galaxy clusters, that dark matter is motion and interaction of space-time. In the last video, I discussed how the properties of structures and interactions can be different between different scalar positions. This is due to all structures being emergent phenomenon of the objects they are made from and what properties they possess. Which means that while the dark matter in galaxies and galactic filaments are made of the same thing, the motion of spacetime, the way it behaves changes with scale. To put even more simply, while galaxies gain more mass from the presence of dark matter, I don't think the universe is gaining any extra mass from dark matter filaments. The difference is that dark matter in galaxies is created from hundreds of billions of massive cosmological bodies, all interacting with each other. And these interactions influence the movement of all the other massive bodies, making them move faster. This causes even more distortions and interactions. It's a system of interactions that positively influences the source of those interactions. But with a galactic filament, at least in the idea I'm proposing, They are created from the interactions of spacetime distortions surrounding galaxies and galaxy clusters. While they can influence the behavior of individual galaxy clusters, these interactions do not appear to increase the rate or velocity of movement, as in, no extra energy is created. Instead, it looks like galactic filaments could be displacing some of the extra mass created at the galactic level to a point between two or more galaxies, which would mean that extra mass isn't being created, but rather redirected to a different location. So it's possible that overall mass either stays the same or is lost in the structures between a galactic filament. This is the connection between the mass of quarks and the mass of galaxies. Most of the mass in an atom doesn't come from the rest energy of quarks simply existing. Rather, it comes from the interactions between quarks. But the interactions between neutrons and protons, or even between individual atoms, does not, in general, increase the mass of the overall structure. In fact, these bonds often reduce the total mass. Which would be the same with dark matter in this explanation. Extra mass is created at the galactic scale because the interactions influence regular matter and causes it to travel at a higher velocity. This creates more energy and more mass in the galaxy. But at larger scales, these interactions cause mass to either be lost or moved away from their source, at least when it comes to gravitational filaments. So interactions between structures can create more mass energy, but not all interactions at all scales will. Whether they will or won't is dependent on how those interactions influence and interact with the structures they were formed from. Maybe the idea I'm proposing sounds plausible, but there's still one really big problem. It would appear to fall apart when considering the early universe. It should be obvious, but there were no large-scale objects like stars or black holes in the early universe to create the kind of distortions in space-time I've discussed. Like most proposed solutions, this one appears to only offer an explanation for the large scale, but says nothing about the small scale or the early universe. However, I'm not saying that large-scale objects cause dark matter, just that the motion and interactions of star systems and other cosmological structures create dark matter at the galactic scale. The more general idea I'm arguing for is that dark matter is caused by the distortions of spacetime that are created from motion and interaction that creates more energy, which appears as mass. All that would be needed then in the early universe would be something that is creating more distortions or interactions in spacetime than from mass alone. In the models of the early universe, gravitational interactions are the most important factor that affected movement. Particles were drawn to dense regions of spacetime, and as particles accumulated in certain regions, it created more gravity that attracted even more particles. But in this dense plasma state, these regions don't coalesce into anything large, because pressure builds up that eventually pushes the dense group of particles outward, which creates sound waves. This process can repeat, where a region of particles can be drawn in, pushed apart, only to be drawn back in again, and so on. Through analysis, it turns out that for particles to clump together as they did would require more mass, or dark matter, to exist in the early universe. For my interpretation to hold, there would need to be some extra movement or fluctuation in spacetime that isn't being accounted for in the standard model. To start, the universe was much smaller, more densely clustered together, and everything was in a hot plasma state, which is where the environment that the particles are in has such a high temperature that electrons, neutrons, and protons can't form into atomic matter. It should be noted that temperature is not a thing unto itself. It's a property that comes about from the motion and energy of particles. When a room is hotter, it's because the particles in the air have more energy than when the room is cooler. So for the universe to be in a plasma, it means that the individual particles must contain more energy. And so we already have somewhere for the extra mass to come from, and it even originates from the motion and interactions of regular matter like our present age, as particles are imbued with more energy from having just come from the Big Bang, which makes them move more readily. This makes the environment more energy dense. Of course, more happened between the Big Bang and the creation of the CMB data, as it wasn't just electrons and quarks that were created after the Big Bang. A whole host of other particles were made that have since decayed. Many of these have very short lifespans and degraded into other particles or just decayed entirely. But there were also antiparticles that were created in vast quantities that interacted with regular matter, annihilating both. Only a tiny fraction of a percent of the matter created in the Big Bang still exists and is what makes up the universe today. which is to say that the early universe was filled with motion and interaction and energy beyond just the regular matter we see in the CMB data. And energy just doesn't disappear, it must be transferred into some other form. What I am proposing then is that in the early universe there was an additional warping of space-time due to the expansion of the universe, the process of particle creation, annihilation, and interaction, and the dense plasma environment the remaining particles maintained. This movement would be maintained and recreated by the normal matter that remained after the creation of the universe. The extra space-time warping around particles encouraged interactions to form between different particles. This increased the formation of structures in the universe by enabling and encouraging interactions between regions dense with matter and energy, which may explain why the amount of dark matter has stayed relatively the same from the early universe to now. It's a consequence of the conservation of momentum, or energy, or something like that. As the universe cooled, that energy got put into creating more complex, dynamic moving systems like galaxies. And now I have finally covered enough background information to return to the other experiments that supposedly prove that the universe is non-local and probabilistic in nature: the Double-Slit experiment and the Mach-Zehnder interferometer. It may seem strange to talk about this here, but it was important for me to fully cover the idea that spacetime is real. Talking about dark matter as spacetime was the final part of that process. The Double-Slit experiment is possibly the most famous quantum experiment to date. If individual photons are shot one at a time through a very small slit in a barrier, they will all be measured in a continuous grouping on a detection plate. However, if individual photons are shot at a barrier with two slits in it that are located very close to one another, then these photons will be measured in a wave interference pattern, meaning that even though only one particle goes through the experiment, it acts as if it interacted with a second particle going through the other slit. It's possible to put a detector on one of the slits that can tell whether or not a particle passes through. And when this is done, the interference pattern disappears no matter which slit the photon goes through. These results can be reproduced using other particles and even large atoms, but not large-scale objects. So at some scale, this property breaks down and matter no longer behaves like this. The current consensus is that the photon is in a superposition of having gone through both slits, and it's the interaction of the wave function of these two superpositions that causes the interference pattern. It's only once the photon hits the detection plate that its waveform collapses and is found in only one location as a single particle, which, according to the standard model, demonstrates the non-local and probabilistic behavior of particles. And then there's the Mach-Zehnder interferometer. This is a setup where individual photons are shot at a beam splitter where each photon has a chance of being sent down one of two paths. These paths lead to a reflecting mirror that redirects photons towards another beam splitter that can lead to one of two detectors. When individual photons are sent through this apparatus one at a time, they will only ever be measured at one detector, even though the second beam splitter can send the photon in either direction. This would be the expected behavior for a particle that is interacting with another photon, because the interference in their wave function would cause them to always go to the same detector. However, only one photon is sent through this apparatus at a time. If a block is placed in one of the paths, then 50% of the time the photon goes down this path and hits the block and no measurement is taken. The other half of the time it goes down the other path and is measured. And here, 25% of the time the photon will be detected at detector 1 and 25% of the time it will be at detector 2, demonstrating that the particle definitely interacts with something at the second beam splitter when there's no block. The standard model explanation is that at the first beam splitter, the photon is put into a superposition of having gone through both paths. At the second beam splitter, the two superpositions interact to create constructive interference in their wave function, directing the photon towards one detector. When there's a block in one of the paths, it's possible for the particle to reach the second beam splitter without interacting with the other superposition. Therefore, it can go to either detector. And this is the problem. These two experiments clearly show that it's possible for an individual particle to behave as if it interacted with another separate particle when none should exist. This is not easily explained by local and real models of the universe. If a single particle went into the experiment, then only that particle should exist in that apparatus. But there is a possible explanation of these results if particles are real in the manner that I've described. What the particles would be interacting with would be the fluctuations in spacetime that they themselves create. These particles would be systems of fluctuating spacetime, which should also warp and distort spacetime around themselves as they move. These distortions should have a physical presence in the universe, even if they're not measurable to us at our scale. But they don't need to be measurable to us. They just need to change the trajectory of photons. The general idea, then, is that when a particle is directed in the middle between two paths, the particle, as a real physical entity, interacts with the pathways. So in the double-slit experiment, the particle only goes through one slit. However, because the particle is displacing and causing fluctuations in the spacetime around itself, it's possible for these to interact with the barrier, and for part of these distortions to go through the other slit. On the other side of the barrier, the particle's wave function interacts with the wave of this distortion, where it can alter the trajectory of that particle. The phase of that particle and the angle of approach could affect the wave functions that go through the barrier. All of this could go into determining where the particle is finally measured at the detection plate, which is what would create the observed interference pattern. This may explain why trying to measure what path the particle took destroys the interference pattern, because in order to measure any particle requires interacting with it in some way. If the particle gets measured going through the slit, then it alters its wave function so that it can no longer create interference with the spacetime distortion. If the spacetime distortion goes through the detection slit, then it could either destroy it, deflect it, or cause it to desync with the particle's wave function. If this is what's happening in the double-slit experiment, then it could also explain the result of the Mach-Zehnder interferometer. We just need to once again assume that particles distort spacetime around themselves, and what is being sent down the other path is just a fluctuating wave of spacetime. So what could happen is that the particle interacts with the beam splitter and goes down one path, and a packet of spacetime fluctuations are sent down the other path as a result of the interaction with the beam splitter and photon. The results obtained from these experiments, then, simply comes from the particle actually going down one path, and a wave of fluctuating spacetime going down the other. When there's no block, the wave function of the particle and wave packet interact. When there is a block, either the particle hits it and there is no measurement, or the wave packet hits it and it is prevented from interacting with the particle. It's sort of like those water wave interference demonstrations, where much of the behavior seen in these quantum experiments can be reproduced, including how objects would move on its surface. Except in this model, the object and the medium it's surrounded by are all fluctuations in spacetime. At least in concept, it would seem to work. I'll conclude with some comments about dark energy. It's possible to use the CMB data to get a value for the expansion rate of the early universe. It's also possible to use measurements of different stars and supernovae to get a value for the current expansion rate. The problem is that the expansion rate of the present era is larger than the rate in the early universe. This shouldn't happen. Because of the effects of gravity, the expansion rate should either stay the same or slow down with time. For this rate to increase over time, a large amount of extra energy would need to exist within the universe. That's dark energy. I actually don't have a lot to say about dark energy, as its presence or absence doesn't affect the overall idea I'm proposing. If dark energy exists, then it's most likely the effects from the movement and interactions of large-scale structures, or from the cumulative motion of matter at the cosmic scale. For example, all of the galaxies in our bubble universe could be rotating around some central point, creating more motion, and hence energy. But I don't want to make any definitive statements about what exists beyond the observable universe, because even if it were possible to know what's beyond this limit, it would take a far more substantial model than this to make any solid claims. So that's really all that I can say. In this model, dark energy could possibly come from the interactions and movement of large-scale structures above the observable universe. However, I want to talk about the possibility that dark energy doesn't even exist. It has been a known possibility for a long time that dark energy might not exist, because it's possible that the value for the expansion rate for the current era could be flawed. This largely comes down to the problem of how it's impossible to make a direct measurement for distant stars and galaxies. There's no measuring stick large enough to get a direct measurement, so proxies are used to gauge distance instead, primarily what is known of the properties of different star types and supernovae. Estimates of distance for different stars is reliable out to a certain distance due to factors like luminosity. So one type of star is used to gauge measurements out to a certain distance because it's the most reliable in this range. Beyond that location, another type of star is used where its distance from Earth is determined from the first star type. And then another, and so on. This goes on until the farthest things that we can measure are analyzed. This whole process depends on cosmologists being right about the properties of these different star systems. Any error or false assumptions will cascade up this ladder towards an incorrect value for the expansion rate. This has always been seen as a possibility. However, no errors have been found with the measurements themselves so far. Even recent data from the James Webb Telescope appears to confirm the validity of these measurements, and so it appears like dark energy really does exist. But there are some researchers who argue against dark energy for other reasons. And this is the reason for the inclusion of this section, as one of the claims is that the researchers who discovered dark energy made an assumption that the universe was homogeneous at way too short of scale. If this assumption isn't made when doing the calculations, then dark energy goes away. The main argument is that the Earth is in an underdense region of space and is traveling much faster than the standard model of cosmology claims. Because the Milky Way is in a bulk flow of galaxies moving towards an overly dense region of space near the Shapley supercluster. This, combined with the rotation around the Sun, and the Sun's orbit around the galaxy, gives the Earth a particular directionality through space. In total, this gives us a kinematic dipole, where there's, on average, one direction that we are moving towards, and one direction we are moving away from. When cosmological observations are compared to this dipole, it appears to show that the Earth is in a region of space that is not like most other places in the universe, and that the universe appears to be anisotropic, which goes against the assumption of isotropy in the standard model of cosmology. But the expansion rate was calculated using the assumption of the cosmological principle. If the math is redone using the observed anisotropy, then the value for the current expansion rate drops, and dark energy goes away. This is a very brief summary of the topic. One of the researchers of this line of thought, Subir Sarkar, has given a number of talks on this work if you'd like to hear more. If it's true that dark energy only appears because of an assumption of homogeneity, then it's possible that dark energy simply doesn't fit in the model I am proposing, as it assumes that the universe is fractal in structure. So, I guess this interpretation would say that it doesn't exist. To conclude, what I am proposing is that dark matter could be motion and interaction within space-time, which on the cosmological scale is caused by the motion of star systems, black holes, and galaxies. In the early universe, this extra mass comes from the motion and interaction from quantum particles in a dense plasma environment. At least it could be under this interpretation where the universe has an infinite scale and space-time is real. And this would link the quantum with the cosmological scale, as everything in the universe would come from the interactions of objects and structures. Extra mass can be created from quarks interacting with each other, and from solar systems and black holes interacting with each other. But there is still the question of how this interpretation meshes with the standard model of quantum physics. This is the biggest problem for all local and real models. So in the next section, I'll discuss what the implications of this idea are for the standard model of quantum mechanics. I hope you will continue to watch.